All right, hey everybody. Um, Going live here in 2690. And first thing I'm going to do is get you a link and drop it onto Discord for anybody coming in live. All right, I'm dropping that on Discord. All right. So that should be okay for that. Okay, what we're going to do today, we're going to wrap up. We actually got to the very end of lecture 12. We're going to finish 12 and then do 13 and 14. And it does actually fit, believe it or not. Let's see. All right, so I talked about these just a little bit briefly on Monday when I talked. RPC as being something that's above sockets as a remote procedure call. The whole idea, just to reiterate, is I want to basically make like I've got a function, it's a library, I link the thing together, and in what I want to be able to do is have the code that I'm running be somewhere else. It really, you can view it as a cloud kind of a thing. You can view it as a remote procedure call, where basically I have some intermediary, and I'll basically, kind of walk through these again. I've got computer A and computer B where I've got a client and a server. And then the client executes this RPC call. Server's waiting for that. So when it gets the call, it starts. Then it performs over on that side the procedure call on that end, then returns it. Then the call terminates and sends back the reply. From the perspective of the client, it's as if it had made a call to a local client, to a local function. Doesn't care, doesn't matter. Okay, that's it. This, by the way, I don't know. The idea shows up in a lot of, remote communications, and it's a good idea to just understand. I don't know how relevant, today. It probably just takes a bunch of different forms. Today this seems a bit more entangled compared to like a REST API or a SOAP API, or even things like Lambda functions in AWS, or other kinds of ways of pushing your computing off to say something in the cloud. And what this does is just illustrates the notion that you've got to have some kind of a stub in the middle, right? So in a normal procedure call, procedure A calls procedure B. But in a remote procedure call, procedure A calls a stub, which is a proxy for procedure B. The stub calls some kind of an RPC protocol, which can then get received by the stub proxy for procedure A on the other side. You can see how tightly coupled this is. That is a little bit of a problem. Okay. Um, but I think the concept is fairly straightforward. And then, so the notion of a stub compiler is just something where you basically set up the interface for how to make a call into this other routine that lives on another machine. And you basically, which we'll talk about, we call that an RPC compiler or an IDL compiler, which is an interface definition language compiler. So this might seem a little strange, right? That you're like, well, how much do you have to know? Well, you don't have to know all the stuff. You just have to know what the name of the routine is, what the parameters are, and what's expected back. Then I can build a little stub that just does that. I'll bundle this per these rules. I'll send it over. Then the work will happen over there. And then over on that side, it's going to receive that, unbundle it, do the work, give me the response back, send it back. So it's really just the wrapper. And if all I have to deal with is the wrapper, then I'm okay doing, compiling that basically. And then this is just an example. And I I don't know how important this winds up being in exam stuff. I don't think it's that important, but if I'll look out at the next exam and we'll decide how much of this to reveal to you and go deep. But, all it's really trying to do is say the name of the remote program, and then what's the first procedure, second procedure, third procedure, fourth procedure, and then the program number of the client and server, which gets used, and which we'll talk about in the next slide set for 13. But all that's really happening is it goes through this RPC gen, takes this RDict. This is just an example of a remote dictionary program. That's why it's called rdict.x. That goes into RPC gen, which creates C files and .h files. It's funky, but it actually creates C code. And then that can be compiled with the client application code is going to talk to it, interface code, and then generate a client executable that can talk RPC, basically. And then on the server side, the same thing happens. That's the idea. And that is the end of module 12. Module 13. So actually, it says it starts with a lecture postmortem, which I'm not going to do today. I want to be able to answer more questions one-on-one when I'm feeling a little bit better. And I'm planning to do this on Monday. So I haven't had a chance to go through the exam grades. So this is where we were before with the specification file coded in interface definition language. This part here, the program number of the client and the server, I want to just sort of show you, and again, I don't even know how important this is, but if you notice this number, 30090949, there it is right here, okay? So that's just a way of attaching a sort of a handle to this thing. And so later on, there's this idea, and I do think that the exam includes something about a port mapper. But this is the RPC client. This is the server machine, okay? And the port mapper essentially is a device that allows the two devices to talk via I/O ports, which it needs to do. Then having received it on an I/O port, it can then map that and get the product or get the thing that's being sent back to the correct program inside the server. That's all that's doing, is discussing this idea that there has to be a mapping function between the program back here, which is program number 30090949, and a port. And it's called an ephemeral port, which is an actual term, believe it or not. It really just means a short-lived port, a port that doesn't persist, okay? And so basically, the client sends an RPC to port mapper on port 111, requests a particular program. The port mapper gives back a temporary port and says, here's how you can talk to that one. So the 111 is sort of well-known. And then I can basically ask this like a well-known directory of sorts. And I can say, here's the program I'm trying to talk to. Here's the program I'm trying to talk to. And then the port mapper can essentially just create a connectivity so that it'll hand me back a temporary port and say, use this one for this RPC call. It'll then use that, and then that'll establish the Endian connection. What you'll notice over and over and over again is that we just keep dealing with abstraction, with levels of abstraction. And this is just yet another way of building on top of ports with, some other mechanism. And then the rest of this, I don't know how much I care. These are just, again, I don't think we're going to do any of this, but I don't think that you need that. This then just gives you an example of some RPC messaging, where you've got a normal UDP header, frame header, IP header, UDP header with source and destination ports. And then here comes the stuff: the RPC request or reply header, the RPC arguments or return value. So, and then this is again another example. So that one was SunRPC. This one again is also SunRPC, just a particular brand of RPC. This is going to basically, have the normal kinds of stuff you'd actually, sorry. This is inside after you've got, an IP packet. And what else? What's relevant? The RPC version, the program version procedure, stuff like that. And then here comes the data, which is the RPC arguments. And then here's similarly, what's the message type? It's a reply. What's the status, etc. Just to, and believe it or not, that's actually 12 right there. And I think it was because I think Dave was originally building in, sorry, that's the end of 13. He was building in time to talk about the exam, which we're going to do on Monday, which I hope would, yeah, we should be able to do that on Monday. And then this brings us to lecture 14, which does a couple of things. We're going to wrap up this discussion with UDP, but then we're going to pivot from chapter 5 to chapter 7. So, all right. This is programming assignment 2. Now, we already talked about it, so this is just where it lives, okay? Programming assignment 1, if you remember, was to write the client and then to talk to the server on the back end. And then we provided the server. Then what you're going to do next is you're going to redo the server, and that's what this is, so that you accept a message from the client that you wrote, okay? So you're basically just replacing the server that was provided for you. That's it. I'm not going to go into it. You know what to do at this point. The specs are over there in program2.pdf. Jump back on Canvas, jump in the files, pull down the stuff. You know what to do. Now, we're going to talk just a little bit about UDP. We talked about TCP and a few things. I like this slide. With TCP, these are just kind of comparisons, and things you do need to understand. For TCP, you need to have a connection that gets established. So you got to set up a connection and then you got to tear it down, okay? With UDP, there is no connection. You just send a packet. If it gets there, it gets there. If it doesn't, it doesn't. With TCP, the connection is reliable. Sorry, I need. With TCP, the connection is reliable. That gives us into things like where I'm going to retransmit if I don't see it, things like that. I'm going to tell you if I lost a packet. UDP, it's unreliable. It's just a best effort. I'm going to try to send it. If it doesn't send, if you don't get it, you don't get it. That's it. The other thing is with TCP, because it's that continuous, reliable, guaranteed sequenced packet delivery, it sets up the idea of a stream. I'm just reading bytes like I read it from a file. Just read some more bytes, read some more bytes. With UDP, I bundle a message, send a message, receive a message. Any other thing I'm going to do, I'm going to build on top of that. Let me see. With TCP, you can assume that any incoming data for a given socket was sent by the computer. And that was the thing we talked about, where you could be, it's more of a secure connection with identity. You know who you were talking to. Whereas with UDP, stuff could come from anywhere. I mean, not likely, but possible. They all use these functions. TCP typically goes connect, then send and receive, whereas UDP does no connection, just goes send to. Here's a destination, send it. Here's a receive from, send it. And again, listen, accept, just a little bit of a difference, send to and receive from in terms of the server. Okay. Now, everything gets really grungy because what we're going to do, this is to set you up, I think, to do the programming assignment. I'm trying to remember because I haven't done it. I haven't built it. You will have the advantage over me there. I believe that this was built in using UDP. So yeah, I'm pretty sure. Man, I hope so now. Yeah, that's right. So this is all just slides to help you build your server. Okay. And we're not going to go deeply through it, kind of like we did last time. Not going to go deeply through it. But this just kind of tells you how it should look like with IPv4 and v6. A little bit more about connection, what you use, send to, receive from, et cetera, et cetera. Okay. It's then going to give you detailed information about send to and receive from. And this has 2 slides. So hence 1 of 2, 2 of 2. All right. And then converting to UDP on the server side, this is just, I think, again, more information about starting with a TCP stream and converting that to UDP. So, I mean, that's really it. And then let me back up to here. Then this also shows you what the Winsock functions are, what the client's going to use, what the server's going to use. All of that is just meant to like hand wave and give you a pointer to the stuff you're going to need to know. And like with the last stuff, it's not going to even make any sense until you actually get your hands on it. So I'm not going to, dive in and go all the way through it. Um, you've got to basically just and I was talking to a buddy about the kind of stuff we're doing in this class and this notion of here's the spec, go do it. And he was like, well, that's kind of like what the real world's like. I mean, it's kind of like what industry's like. You want to do data communications, no one's going to tell you how to do it. You're going to get the doc. You're going to understand the basic ideas. These are the calls. Drop them in, get hello world working, get your make file working or your build working so you can build something. And then you're just going to slowly get one thing done, make sure that it works. And again, same thing I told you last time. I strongly, strongly recommend get one thing done and make sure it works. Get the next thing done, make sure it works. Don't code the whole stinking thing and then wonder why it breaks and you have no idea where it breaks. Get one thing done and verify that it works. Okay, and then some additional resource material. Good luck. These are actually kind of fun projects. So I haven't done these assignments, but I have done professionally written code using sockets, using ports, built my own protocols, my own sort of session layer protocols, designed the protocols myself, built them, got them working over TCP and other, similar protocols like SPX. And so I've done stuff like this. I'm just not, and I won't just because of time, where I'm at on, this semester. But I've done it and I know if you understand the concepts and you build on that slowly, you'll get it. And it'll be really, really cool. And then by virtue of using the loopback address, you don't need to set up it's a much more simplified, uh, sort of configuration. Which brings us to a color change, which is chapter 7, and we're still in slide lecture 14. This goes 19 slides to slide 19, okay? So this is not bad. This isn't too bad, and we'll wrap up here pretty quickly. This is not so bad to get caught up. The idea that we're talking about here is presentation layer functions. This is chapter 7 of your book. On top of RPCs live a number of things, okay, a number of features. One that you kind of already have an understanding about is encryption. Another one is compression, right? Sending a large file and having it be compressed and then decompressed. And then presentation formatting, which we're going to talk about. This is the equivalent for the OSI layers. Again, I think you must have hit OSI in Networks 1. So there are different kinds of standards, okay? And that's what this is really about. I don't think you need to like remember all these, but you should recognize a number of these. One are the standards that define data types. So XML, you should be aware of Unicode, you should be aware of ASCII, which we learned in 2810. These are just standards that all a standard says is, go back to any of you that had 2810 from me. A standard is just a social contract. We just agree that that's how we're going to do it. That's all it is. And so ASCII is just a way that we agree that if we know that we're both using ASCII, then we know what stuff means. That's it. Document level standards are higher level, like, for example, HTML, like markup languages, MPEG, PDF files, RTF files, MP3s, JPEGs. Those are standards, but they're at a document level. So we agree that this file I just sent you is a PDF file, then you know what to do with it if you understand PDF. It's a social contract, okay? These become important now when you're dealing with a presentation layer. So basically, I got some app, right? And I save it as a PDF. I send that in a series of messages. It gets reconstructed back into a PDF on the other side. And then the application on the other side can deal with it. Pretty straightforward. Similarly, I'm building, I'm writing a document in Unicode. I save it to a Word doc. I get to the other side. I know it's a Word doc. I know it's using Unicode. And then the application can now use it. All right. Now, it turns out that there are innate incompatibilities. I mean, like I said, you go back to here and you've got a lot of different file standards, but you've got a lot of, different data type standards. But it turns out that even at the hardware level, there are different incompatibilities. Okay. For example, how big is an integer? 16, 32, 64? Is a number signed or unsigned? If it's signed, is it 2's complement? And then we're going to talk about big or little endian. We briefly touched on it, and I assumed you must have hit it last semester in Networks 1. I don't know, but we will talk about it. What's your floating point standard? What's the standard for a character? Is it double byte Unicode? Et cetera, et cetera, et cetera, et cetera. And so there are data type incompatibility. Just remember that. Just keep that in mind. And you have to, be aware of that when you're communicating with another system, that you just can't assume that the whole world is 16-bit integers. And that comes into play when you start talking about RPC, right? I'm going to send an integer to something that was built on another machine. It needs to be the same kind of integer. Now, this is little endian versus Big-Endian, and there's a homework which you're on your own. You know where this is now. So jump on homeworks questions 9 and A, and there's 2 slides on Big-Endian and little endian, and that is the end of this slide set. Okay, so I want to just talk about these for a second, and I want to start over here actually. Big-Endian means essentially the question is I've got a multi-byte value. like a multi-byte integer, which end do I transmit first? That's the question, okay? Do I start at the big end and do I chunk it going from big to small by, higher order to lower order, or do I send it lower order to higher order? It's an issue where when I'm working within an architecture, it doesn't matter because it's going to be consistent within a machine. But now we're sending integers, or we could be sending a 64-bit long integer to another machine. Well, what's the format on that machine? And it turns out on the second bullet that integer values stored in little endian systems like Windows and Intel have to be converted to Big-Endian using functions designed to do that, okay? So you just have to understand that if I'm going to send a 4-byte integer, 2-byte integer, any multi-byte integer, and I'm sending from a Windows machine, or I'm supposed to put an integer into some header where it expects Big-Endian, I have to switch the bytes. So this is important. If these are 4 bytes, I just switch the order in which I send them. But it's more like, it's kind of like each byte still gets transmitted as a single byte, but the order of the bytes is different. So the byte is still high order to low order. That doesn't get switched. But the order in which the bytes get sent, that's all you have to know about Big-Endian and Little Endian. Okay? And so that's what this is trying to show you, that these are the values, a Big-Endian representation of that value, 00, F2, 04, 01, all in hex, right? These bit patterns. That's a Big-Endian representation, and that's a Little Endian representation. And notice that the bits are in the same order, but the bytes are swapped, okay? And you're like, again, you got to have a sense of why that matters. It matters because some architectures store multi-byte values in Big-Endian and some store it in Little Endian. If I then just send that, right? If I send that value, if I send 00FF, so I'm a Big-Endian machine, right? And I send it over to an Intel machine. I'm sending from, I don't know what I'm sending it from. And I send it to an Intel-based machine. And it receives 00F20401, receives it in that order. But because it's a Little Endian representation, it assumes a reverse order. So the system's just going to have it backwards. So you have to, so basically everything that gets sent across that if you're just sending a byte stream, I don't care. But if I'm sending something that we both agree is a multi-byte value, that is a single value, I'm going to send it Big-Endian. Okay? That's the bottom line. I've got to convert it to Big-Endian. And by the way, it is Endian, as in the big end, little end, the shallow end, the deep end. It is not Big-Endian and Little Endian. Okay? It is Big-Endian, Little Endian. It's weird terminology. That's it. That's all you need to know. And one way to double check that, is but be aware of this as you're doing the assignment. I think there might be some information in the assignment about it, but be aware as you're doing this, okay? All right, there's your homework. And that, my friends, is the end of lecture 14. So we actually did successfully get through 11 and 12, 13 and 14 during this week. The only thing we didn't do is the exam review, which I'll get to on Monday. And then next week, what we need to get through is lectures 15, 16, and 17, at which point we will actually be caught up with the schedule. That's all I got, my friends. I'm going to wrap and ping me on Discord. There's been some good discussion on Discord where people have questions, and be sure to help each other within the bounds of not cheating. Don't answer don't do other people's work for them, but clarifying questions, super helpful. So, alrighty, I'll talk to you later.